Well, we'll just do an example. It was 28 assigned? Somebody give me. There were a couple here that I hadn't covered those types because I didn't think we were going to. I don't have them with me. 24. 24 you should be able to do. What else? 21, 24. What else was that? 31. Oh, 31 you have to do division. And 30? Okay. So there's a couple of things. So you have to look at the factors of the denominator. So suppose you have, this was 24, those are the factors in the denominator, right? Right. But we don't care about the dx for the moment, okay? We want to figure out how to break that up. So when you take the x cubed minus x, you can factor it into this. So you have three terms. So you're going to need a over x plus b over x plus 1 plus c over x minus 1. Okay? So you're going to end up with three equations and three variables. I won't do all the steps for you, but a is going to get multiplied by these two. So a is going to be times x plus 1, x minus 1. B is going to get multiplied by x and x minus 1. And C is going to get multiplied by x and x plus 1. And that's going to equal x squared plus 2x minus 1. We love these, right? No? Don't love the algebra? Think so. So, skipping a step. You should get that. You guys saw I put up a whole bunch of problems over vacation. There was one small type I didn't do, which was those trig substitutions. I'll do some of those this week, so you can practice. The exam's in a couple weeks, right? I don't know how much more we're going to get to before the exam. I guess we'll do areas and volumes. And then we'll have some time for review. I'm looking to see if I can get a classroom to do an extra review session, but it's tricky, because I could get like a review for, say, 12 of you, and then I could pick the ones I like best, which usually you demonstrate with chocolate. Or, of course, gold work. But to get a room for, say, 250 of you sometimes takes a little maneuvering. Alright, so now we have ax squared and bx squared and cx squared. We have bx and cx. And we have minus a. And that's got to equal x squared plus 2x minus 1. So you're going to have a plus b plus c has to equal 1, because it's 1x squared. Minus b plus c will have to equal 2. And you know what a is. You know minus a equals minus 1, so you know a equals 1. So you should be able to solve from there. Okay? And then you're going to get something over x plus 1, and something over x minus 1. Not going to do every step. Now, there was a long division one. Did that give you 30 or 31? 30. You win. I'm going to show you a cheat. Now, I'm going to show you a trick first, which most of you probably won't really pick up on, but that's okay. So you take the numerator, and you subtract 16, and you add 16. And you go, why would I do that? Well, you'll see. You could break that into r squared minus 16 over r plus 4 plus 16 over r plus 4. Now, does r squared minus 16 factor? R plus 4, r minus 4. I hate making r's. They're very hard to do in chalk. And then those cancel, and this integral becomes r minus 4 plus 16 over r plus 4, which is a very simple integral, right? R squared over 2, 4r, 16 times the log of r plus 4. Now you say to me, but I would never know that trick. Right? Can you guys see what I did? So I subtracted 16 and I added 16, and that enabled me to write two integrals, two fractions, and the first I can simplify. Now many of you would say I would never think of doing that. That's okay. The other way is you do polynomial, you do division. Okay? Or you can do synthetic division, for those of you who remember synthetic division, which is more fun. Okay? So r goes into r squared r times, because r times r is r squared. You multiply them together and subtract, and you get minus 4r. Did I do that right? Yeah. And there's no, it doesn't, sorry, right. Okay, you bring down the 0, that's a 0. And now minus 4 times r is minus 4r, so this becomes minus 4r minus 16. Subtract, and you get 16. Since r plus 4 doesn't go to 16, you get that. So you can end up in the same place. So we math geeks know a lot of shortcuts that you guys probably don't know. But that's okay. And this, as I said, this you should be able to integrate very simply. I hope so. So again, if you want to do the polynomial division, you say how many times does r go into r squared? Well, r times r gives you r squared. So you multiply it out, you get r squared plus 4r. You subtract, and you get minus 4r plus 0. And then minus 4 times r gives you minus 4r, so you multiply the minus 4 by both terms. And you subtract. Okay? That's the polynomial division. And if you had x squared plus 4 and x cubed plus 4, that's a nasty one. I never teach these. They're hard. But you should be able to do them once you get the hang of them. So if you want to do there's other clever tricks, but let's just do the division. So you want to do x squared plus 4 goes into x cubed plus 0x squared plus 0x plus 4. You have to have a 0 for all those missing powers of x. So x squared times what gives you x cubed? X squared times x. So this is x cubed plus 4x. And subtract. And you get minus 4x plus 4. Now x squared doesn't go into minus 4x. So this is minus 4x plus 4 over x squared plus 4. So this integral would become integral of x plus negative 4x plus 4 over x squared plus 4 dx. Everybody following me? You guys are all being very quiet. Hi. Okay. So So this would now become x minus 4x over x squared plus 4 plus 4 over x squared plus 4 dx. So this is easy. This is just x squared over 2. This you can do with substitution. That's inverse tan. Okay? I'm leaving that part up to you guys. How are we doing on these? They're hard. Okay? We'll do a couple more. I'll do some of the appendix G ones. I forget which ones were assigned from appendix G. Somebody say that. You can tell me. 20 what? Okay. Okay, what do we do with the first one? Well, this we didn't do this type yet, so we should learn this. The bottom here factors in x squared times x plus 2. So we have x squared, it's slightly different because you have what's called a repeated term in the integration, or in other words, in the denominator. So now you would have to make this a over x plus b over x squared plus c over x plus 2. So when you have a term and it's been squared, you do once over the term and then again over the term squared. So if it was cubed, you have a over x, b over x squared, and c over x cubed. Got the idea? So if you have a denominator and it has like an x plus 1 squared in it, then you would do an a over x plus 1, and you do a b over x plus 1 squared. Okay? And the handwriting's a little off today. Make that look prettier. Okay? Yes? Well, it has to do with the way you can put the rational expression together. So when you have a repeated factor in the denominator, a factor that's raised to a power, you have to take one letter over the factor and then another letter over the factor squared. If it was cubed, you'd have to have a third letter over the factor cubed. Okay? So as I said, so if you had something over x plus 1 squared, you'd have to have a letter over x plus 1 and a letter over x plus 1 squared. So that's the way this would break up. So you would have 5x squared plus 3x minus 2 over x squared times x plus 2 equals a over x plus b over x squared plus c over x plus 2. And that takes a little algebra. The a gets multiplied by x squared and x plus 2. So let's see, you have 5x squared plus 3x minus 2 and then you get b. I'm sorry, a only needs to get multiplied by x, sorry. Because when you multiply through by x squared, the x squared cancels with the x. Okay. B just gets multiplied by x plus 2, and c gets multiplied by x squared. That's what happens when you multiply through by x squared times x plus 2, and you clear the denominators. Okay? So again, so the a gets multiplied by x, and x plus 2, b by x plus 2, and c by x squared, and then everything has the denominator of x squared and x plus 2. Yeah? Lost?
Yes.
We're lost. I'll write the intermediate step. Okay? So I have a over x times x squared x plus 2 plus b over x squared times x squared x plus 2 plus c over x plus 2 times x squared x plus 2. Okay? And in the first one of the x's cancels. So you get 5x squared plus 3x minus 2 a times x is x plus 2 plus b, the x squareds just cancel. This times x plus 2. And c, the x plus 2's cancel, and c is just multiplied by x squared. Well, you want a common denominator, so what would the common denominator be? It would be x squared x plus 2. So b really only needs to get multiplied by x plus 2 to make a common denominator. Right? It's already got x squared in the denominator. Right? Common denominator is this, right? Right. Well, no, b gets multiplied. Everything can get multiplied through by the same thing. If you multiply through by the common denominator, which is x squared times x plus 2, and then you do the canceling, you end up here. Okay? I know, you're not totally satisfied. Look, the common denominator is x squared times x plus 2, right? You already have b over x squared. So you really just have to multiply top and bottom by x plus 2. Right? Then everything would have the denominator of x squared times x plus 2. So b only needs to get multiplied by x plus 2. Right. You're multiplying through by the denominator of the left side. Clear the denominator, so there's no fractions. So, you have 5x squared plus 3. I find these problems exhausting. This is ax squared plus 2ax plus bx plus 2b plus cx squared. So that's a plus c has to equal 5. 2a plus b equals 3. And 2b equals negative 2. So we know b equals negative 1. That makes a equal to 2 and c equal to 3. I'll let you check that in your spare time. That means we can rewrite this of 2 over x plus minus dx over x squared plus dx over x plus 2. Okay? Those are all very straightforward integrals. The middle one is minus, because it's minus 1. I know I'm skipping some steps. You guys have to fill in the intermediate steps. Okay? Alright, I'll do one completely. Oh God. What were they, 24 and 30? How many is 30? Oh, 31. Alright, I'll do 31 completely. That's going to take a couple minutes. And then when I get to the new material. Maybe you guys will get this. Okay. X squared plus 4 squared. Alright, this one's going to really not be fun. Are you ready? So notice I have an A over X. Then I have a term of X squared plus 4, so that needs a dx plus C. But wait, X squared plus 4 is squared, so I need a dx plus E. Yeah, I'm not happy either. Over X squared plus 4 squared. Which, by the way, is X to the 4th plus 8X squared plus 16, just for future reference. So this is 1 over X times X squared plus 4 squared is going to be A is going to need to be multiplied by X squared plus 4 squared. So A is going to get multiplied by this, X to the 4th plus 8X squared plus 16. Bx plus C already has an X squared plus 4, so it just needs to get multiplied by X and X squared plus 4. And Cx plus D is already over X squared plus 4 squared, so it only needs to get multiplied by X. Not as bad as it looks, because remember over here, everything is 0. It's 0x to the 4th, 0x cubed, 0x squared, 0x. There's only 1. So maybe it won't turn out so bad when the time comes. Alright. So I've got ax to the 4th plus 8ax squared plus 16a plus bx times x. Oh, wow. Let's see. Who picked this problem? And of course the left side is really only 1. So you get 1 is ax to the 4th plus 8ax squared plus 16a plus bx to the 4th plus 4bx squared plus cx cubed plus 4cx plus cx squared plus dx. Wait, I lost something. This should be dx plus e, sorry. Is that what you're going to ask me now? Okay, so far so good. Who's lost? Everybody. So again, because you have x squared plus 4, you need a something x plus something. And then because it's squared, you need another something x plus something over the term squared. Then your common denominator is x times x squared plus 4 squared. So when you multiply through, a gets multiplied by x squared plus 4 squared. Bx plus c gets multiplied by x and x squared plus 4. And dx plus e just gets multiplied by x. Yes, Paige?
Why does the b and the x, like when it's a plus bx plus c, what's the...
Well, the common denominator is x times x squared plus 4 squared, right? So a already has an x, right? bx plus c gets multiplied by x and x squared plus 4, and dx plus e already has an x squared plus 4 squared, so it only needs to get multiplied by x.
No, like on the top, like why is a plus bx plus c and not a plus b plus c? You know what I'm saying? Never mind.
Why aren't these all together?
No, never mind.
Why is it bx plus c and not b?
Yeah, why does it have an x on it? Why does b have an x on it?
Why is this b x plus c rather than just b?
Yeah.
Well, we did this last time. When you have a quadratic factor that can't be reduced, reduced, you need an x term and a constant term. Okay? So if you had x squared, you'd still need bx plus c. Well, not really. If you had x squared plus something, okay, you need a bx plus c, and if it's squared, you need a dx plus e term. So this mess turns into, let's see, the fourth power terms are a plus b, they have to be 0. The cubic term, c has to be 0. That makes life easier. The quadratic terms are 8a plus 4b plus d, that has to be 0. Everything is 0 except for the constant term. The linear terms are 4c plus e. That has to equal 0. And then 16a has to equal 1. So now we know a is 1/16. And since a plus b is 0, b is minus a 16. We already know c is 0. And 4c plus e is 0, so e is 0. And d, let's see, that would be 8/16 is a half, minus a quarter, so that's a quarter plus d is 0. So d is minus a quarter. Okay, I'll let you solve those again on your own. Those are your equations. That means that this integral, dx over x times x squared plus 4 squared equals a over x, so 1/16 dx over x, plus bx plus c, well c is 0, so minus 16 x plus 0 over x squared plus 4 plus dx plus e, so minus a quarter x over x squared plus 4 squared. Glad you came to class today, huh? I was hoping for snow. I was. So again, I just pulled the 16th out and I pulled the quarter out, okay? That's why these are sitting out here. And C and E both came out 0. So when you have your bx plus c and your dx plus c, those both go away. You did turn the camera on, right, Michelle?
Yes.
And you turned the sound on?
Yes.
Okay, good. Alright, so this is 1/16 natural log of x minus 1/16. Alright, you should practice making sure you can do that middle integral. Alright, that is a basic u substitution integral. Let u equal x squared plus 4 du is 2x dx, so 1/2 du is x dx. Make sure you can do one of those integrals. Integral of x over x squared plus something. So this integral now becomes 1/2 du over u. And look, I can use the same substitution for this integral. This just becomes 1/2 du over u squared. Some of you are nodding your heads, others of you are crying. Okay, minus the 16th times minus a half is minus a 32nd ln of u minus an 8th. What's the integral of du over u squared? Well, that's just u to the minus 2 du So that's u to the minus 1 over minus 1. Also known as negative 1 over u. So this becomes minus 1 over x squared plus 4 plus a constant. And then you substitute back for u, and you get 1/16 log of x minus 1/32 log of x squared plus 4 plus 1/8 times 1 over x squared plus 4 plus c. Okay? You're allowed to hate these. If you practice the partial fractions, you will get good at them. They're really just a lot of algebra. They're actually not that hard calculus-wise. It's just hard algebra-wise. I can't imagine we would ask one like this in the test. I don't know, since I'm not writing the test. But it's a lot of work. I mean, look at all those steps. And I skipped a couple of steps in the middle. Alright, time to learn something new. I know. I love learning new stuff. Any other questions before we get going? If I do have a review session, it might be on a Saturday or a Sunday. I will warn you, because I might not be able to get the room during the week. Okay? If I have to choose between Saturday and Sunday, Saturday, Sunday. Oh, there you go. That's easy. All right. Who didn't vote? You didn't vote. What'd you vote for? You vote for both. Can't vote for both. Gotta pick Sanders or somebody. Oh wait, there's another guy running. The orange guy. What's his name again? Anyway, America's a great country. One of my ex-high school students went to McGill and he's emailing me and saying, I'm not in America anymore. And I said, don't come back for a long time. He's a Canadian citizen. You know what college costs in Canada if you're a Canadian citizen? Nothing. You even get free books. Alright. Now, new type of integral. Now the integration isn't actually very complicated. It's just you have to learn to think about another type of integral. So what if I wanted to integrate something very simple? Just want to integrate 1 over x squared. But I'm going to integrate it from 1 to infinity. You go infinity, what do I do if I have infinity? Okay, because we can integrate 1 over x squared, right? Integral 1 over x squared, we're going to do it in a minute, it's very straightforward. But what do I do about the fact that it's infinite? So this is something called an improper integral. This is the last integration technique thing we do. After this, we're going to do applications. I know. It's going to be very exciting. You're going to learn areas, and then you're going to spin those areas around the axis and make pretty volumes. So how would we do that? Well, you can't really plug in an infinity because it's infinite. So what you do is you make up a letter. What letter should I use? How about C for Chris? So I do, because he was yawning just now. So what I'm going to do is I'm going to do the integral from 1 to C, and then I'm going to take the limit as C goes to infinity. Okay? So when I'm just going to do the integration, then I'm going to do from 1 to C, and then when I'm all done, I'm going to take the limit. So what I recommend is that you break this up into pieces. So first, just do the integral of 1 over x squared dx. That's the integral of x to the minus 2 dx. So what's the integral of x to the minus 2? Well, that's x to the minus 1. over minus 1, I had it over there, also known as negative 1 over x. You'll see that? You can differentiate it if you're not sure. So I'm ignoring the 1 to c and I'm ignoring the limit per minute. So now I've done the integration. So the integral of 1 over x squared, I make that x to the minus 2. And the integral of x to the minus 2 is x to the minus 1 over minus 1. X to the minus 1 is 1 over x. Now, I'm going to do the limit as c goes to infinity of minus 1 over x from 1 to c. That is, you plug in the c, you get minus 1 over c plus 1 over 1. And now, what's the limit as c goes to infinity of 1 over c? Do you see that down there? Well, as c goes to infinity, this limit is 0, 1 over c, so this just equals 1. Okay? So that integral is 1. Because it's minus, where is it? I plug in 1 and 1 over 1, but it's minus minus, so it becomes plus. Remember, it's the top one minus the bottom one. I'm plugging in c, I get minus 1 over c, minus 1 over 1. Then I take the limit. We'll do a couple more of these. Don't worry, I won't abandon you on the first one. Okay? Yes? So this converges to 1. So the magic thing you're trying to figure out is whether the integral converges or diverges. And for those of you who are going to take MAT127, you're going to see converging and diverging a lot. So one way to think about converging is if you imagine some horizontal asymptote somewhere, okay? It means that when you calculate the area, as the top gets bigger and bigger and bigger, it approaches a horizontal asymptote, but it doesn't get above that horizontal asymptote. That number, that asymptote, is what it converges to. Okay? That means it converges if it has a number that it gets closer and closer to, without actually getting there. Okay? So, if you did from 1 to a trillion, you'd get very close to 1. Okay? If you did 1 to a Google, you get really close to 1. But you wouldn't actually get to 1. You just get lots of 0.9999s all the way out. Okay? If it diverges, that means the area just gets bigger and bigger. Okay? So you really just need to figure out, does it converge or does it diverge? Okay? Let's do a couple more. One of the problems with this book is it lacks for examples. All right. What if I do the integral of 1 to infinity of dx over x plus 4? So again, you rewrite this with a limit. Let's see. I give partial credit for writing the limit, but, depends on the professor. Let's make up a new letter. How about M? It doesn't matter what letter you pick. I advise against S. Okay? So the limit as n goes to infinity of 1 to m dx over x plus 4. So again, ignore the limit and the limits of the integral for a minute, and just do the basic integral. So the integral dx over x plus 4 is the log x plus 4. Right? So this is going to become limit as n goes to infinity of ln of x plus 4 from 1 to m. That's going to be the limit as n goes to infinity of ln of m plus 4 minus ln of 5. Don't need the absolute value bars, because the absolute value of 5 is 5. You don't get partial credit if you know that the absolute value of 5 is 5. Sorry. Okay, now what happens as n goes to infinity to the log of m plus 4? You do the log of infinity, and that's infinity. Right? So this becomes infinite, so this diverges, so you're done. It doesn't matter what the other number is. Okay? So once you get to the integral, and part of it becomes infinite, then the whole thing is infinite, and forget it. Okay? Yes? You should write diverges. Okay? Well, it's tricky because divergent, you have to do infinite sums. Divergent series can have all sorts of different solutions when you sum them. Okay? So write divergent, like the movie. Okay? Convergent, divergent, allegiance, insurgent, detergent, I think was the next one. Now here's a rule of thumb. This isn't true for everything, but if you have that kind of integral, okay? And by the way, x to the 4 could just as easily be x, okay? If okay? You will find that that is generally true. Okay, oh, sorry. Now be careful, because there's lots of other types of integrals we can give you. But if you have the integral from 1 to infinity of dx over x to the p, and p is less than or equal to 1, it will diverge, and if it's greater than 1, it will converge. Alright, let's have you guys practice one. That's good. There you go. Let's see if you guys can do that one. Be careful. So again, you would want to write this with a limit. Let's see, how about I use B? Later somebody's going to ask why I use different letters. The answer is why not? There's no reason to use different letters. You can use the same every time. As I said, I would stay away from letters like X, Y, and Z. Don't you hate it when cell phones ring in class and you're talking? Okay, so I would make this that's the Beatles. You guys are T.O. You don't remember the Beatles. Alright. So now let's just integrate dx over x squared plus 1. That's inverse tan of x. Okay? There's no x up here. It's not a log. It's just x squared plus 1 in the bottom. So this is the limit as x goes to infinity, as b goes to infinity, of tan inverse of x from 0 to b. Okay. So that's the limit as b goes to infinity, tan inverse of b minus tan inverse of 0. Okay, what's the tan inverse of 0? Tan inverse of 0 is 0, because the tangent of 0 is 0, right? Here's the fun part. What's the tan inverse of infinity? Who got that? Tan inverse of infinity is pi over 2. Because the tangent of pi over 2 is infinity. Now why would I do a problem like that? Because I hate you, and I wanted to make you suffer. Because you should expect something like that, okay? It's fair game. So, when you see infinity, the tan inverse of infinity is pi over 2 because tangent of pi over 2 is infinity. Okay, that was entertaining. Let's do some more. Yes. This converges. It converges to pi over 2. Okay? If you get an answer, it converges. It's only when you get infinity, then it diverges. Alright, what if I had The integral from minus infinity to 0 of x e to the x. You guys want to try this on your own first?
No.
No? Yes? We get some no's on the left, we got some yeses on the right. Some maybes in the middle. Well, let's see. First, let's just set this up. I will use A this time. Should we do minus infinity or infinity? Let's see. We'll do minus infinity. From A to 0, x e to the x dx. So I'm going to have to integrate x e to the x dx. How do I integrate that? Integration by parts. So much fun. Hey, we taught it to you for a reason. I know, you really wish you were still on vacation. Working on the tan. Well, okay, why don't you try integrating that for a minute? Make sure you can integrate x e to the x. I would let you equal x, but, you can do what you want. Paige, you got it? Okay. Yes? No? Copy up the page. Let u equal x and v equal e to the x dx. You got it? Who got it? You got it. Alright, that's long enough. So let's let u equal x. dv is then dx. du is, sorry, dx. dv is e to the x dx. And v is e to the x. So you can rewrite this as u times v minus the integral of v du. And that is x e to the x, and the integral of e to the x is e to the x. Okay? So this becomes limit a goes to negative infinity of x e to the x minus e to the x from a to 0. Plugging in 0 is always fun. So the limit a goes to infinity of 0 minus e to the 0 minus a e to the a minus e to the a. That's to minus infinity, not plus infinity. All right. Okay. So minus 1 is easy. When I do minus infinity, what is e to the minus infinity? That's 1 over e to the infinity, which is 1 over infinity, which is 0. So this is going to go away. That's just minus 1. So this is the only tricky part. So how do you integrate a e to the a as a goes to minus infinity? I'm sorry, not integrate. How do you take the limit? Got any ideas? Well, what you can do, it's going to come out 0, is you can make this the limit as a goes to minus infinity, or just a plain old infinity, of minus a over e to the a. That makes sense? Because at minus infinity, right, that's minus 1 over infinity. So you can do it this way. Then you do L'Hopital's rule. You remember L'Hopital's rule. Just take the derivative at the top and bottom. And that equals 0. So this is 0. This is 0. The whole thing comes out negative 1. Yes? Well, you can't do 0 times infinity. Okay? That's the problem. So you have to make it, you have to be able to figure out the ratio. But as a general rule, if you have a term like x or something in the numerator, and you have an e to the x in the denominator, as you go to infinity, it's going to go to 0. Because the e term is going to get there. It's going to get much bigger than the numerator. Yes? Here, can you factor out the e to the a? Oh, here. Yeah, so, sure, you can take it out. You'd end up in the same spot. You would. Try it and see. All right. We'll do one other type, and then Wednesday we'll do some more of these, because these are way too much fun. Well, that was fun. Okay, here's one for you guys to do. There you go, that'll keep you busy for a minute. Now think about this geometrically. What does that mean if I'm doing from 2 pi to infinity of sine of theta? right? Got the area, and I'm going to have the piece below, piece above, and the piece below, piece above, right? So aren't they going to all cancel? Well, what if I have one left over at the end? How would I know? How do I know where I stop? Do I know where I stop? It's going to infinity. There is no stop, right? That should diverge, okay? It should diverge because it's just, if you imagine this, right? Well, every one of these areas cancels with every one of these areas. This is the problem with divergence, why you can't really write infinity or things like that. So each one of those is going to cancel, but the problem is I'm going to infinity. So there really isn't a stopping point. So if I stopped there, I would get a positive area. If I stopped, well, I can't ever really get it negative, right? If I stopped here, I would get a different area. And well, do I have more negatives? Do I have more positives? You don't really know, and therefore, it's going to diverge. Now, you can integrate it and see, okay? Where would I do it? I'll do it over here. So the limit as w goes to infinity, 2 pi to w, sine of theta d theta is the limit as w goes to infinity minus cosine theta from 2 pi to w. That's the limit w goes to infinity minus cosine of w plus cosine of 2 pi. So even though cosine of 2 pi is 1, the limit as w goes to infinity of cosine of w is infinity, so you can stop. Okay? So this one is divergent. Is the new movie any good? Because the first one wasn't so great. The second one wasn't so great. Books were better. Somebody must have seen it. What is cosine of infinity? It's divergent. You don't know what cosine of infinity is. Right? It oscillates, so it goes on forever. Well, it has some value, but you don't know what the value is. Since you can't pin it down, you can't say what the integral is going to be. Okay? As I said, you can't pick what the area is going to come at. Okay? I think that's enough for today. We'll do some more of this stuff on Wednesday.